All right, so now we've got our planets created. What about the rest of it? How are we going to get the rest of that cloud not in our solar system anymore? How are we going to get rid of that extra material, right? You probably noticed there's not a big cloud out there in our solar system. We don't talk about that. We talk about the fact that there are planets, there are asteroids, there are dwarf planets, but we don't talk about these big clouds of stuff that's out there because they're not there. So how are we going to get the rest of this nebula out of here? To clear this nebula out, we're going to use the radiation pressure from the sun. What this means are the photons from the sun, right? The light, remember, photons are particles of light. These photons are actually going to push some of that material out of our system. Seems kind of surprising that something like a photon could push material, right? Remember, photons don't have any mass. They're not really anything. But these photons have enough momentum that they can move that material out of our system. We're also going to use what's called the solar wind. The solar wind is an actual stream of material that's coming off of our sun. All stars have this. This stream of material, little charged particles and things, can actually help to push that gas away as well. We also had the sweeping up of debris by the planets that are out there. We see evidence of that on all of the hard surfaces that are out there in our solar system. Right? All of these crater marks are from these planets picking up all the little tiny pieces that were left over as they went around. And then finally, not too common, but there were ejections. Let's say there was a little piece of rock and it got a little bit too close to maybe Jupiter or Saturn. If it gets too close in just the right way, it can make its orbit change so violently that it'll get flung out of our solar system. So that did also happen to some of those bodies that were out there. Okay. This cratering, we see it on all of the solid surfaces that are out there. We, of course, don't see it on the Jovian planets, because remember, those are our gas planets. If a rock hits a cloud, it doesn't leave a mark. Okay. So on our Jovian planets, we don't have a permanent record of this period of cleaning out the solar system, but we definitely do on some of the other objects that are out there, such as Mercury and the moon, as shown here. Now, not all of those bits got cleaned up, though. Like any good art project, there are always leftovers. Okay? Those leftover pieces are what we call the asteroids and the comets. Okay? So asteroids are rocky bits, right? Little leftover rocky pieces. Those are the ones that were most likely formed inside the frost line. Now, asteroids can have some ice in them, but they're much more rock than they are ice. Okay, so those are the ones that we find in the asteroid belt, just in between Mars and Jupiter, just inside that frost line. Way out on the edge of our solar system, we have objects, these icy objects. We usually know them as comets, but most of the time they're just little rocky, icy chunks that are out there on the outside of the Jovian planet's orbits, right, out there past Neptune. These are the icy counterparts to our interior asteroids. Okay, so same sort of idea, they're leftover pieces, but these are leftover icy rocky pieces because they formed past that frost line. So let's take a look at some of those space debris that are out there. We'll take a closer look at them as we go. Here's some nice images of an asteroid. This is asteroid Eros. It's interesting to notice that even these asteroids have craters. Okay? Every surface that's solid in our solar system shows evidence of this cratering. Here's some images of comets, right? Don't they look lovely? Okay? They don't normally look like this. This only happens with this big tail out here. This only happens when they get close to the sun. Most of the time they look much more like those asteroids do out there. Okay? We'll take a look more at what's going on with our comets in a bit. We also have the little tiny pieces. Okay, so meteoroids, right? Notice the oids in here, right? Not meteorites, but meteoroids, like asteroids. Okay, meteoroids are little tiny pieces of debris that's out there. Okay, now, the definition I've always heard is we're talking one atom to something smaller than an asteroid, which is pretty vague. But most of these meteoroids are pretty small items that are out there. And there's lots of little pieces, right? It's like doing a craft project with glitter. You never get it all cleaned up. These little meteoroids are like the little glitter pieces out there, right? They're just everywhere out there. We usually experience these here on Earth as a meteor. If you've ever seen what we call a shooting star, that's one of these little pieces of debris hitting our atmosphere and making that nice little flash of light across the sky. That's what you're seeing here. So this is a meteor here, right? When a little meteoroid hits our atmosphere, it creates what's known as a meteor. Let's talk about the age of our solar system. Okay. Because all of the system formed at the same time, we would expect that the entire system should have roughly the same age. Okay, now some of the planets form maybe a little bit ahead of the others, but only by a tiny amount. Okay, pretty much everything has the same age that's out there. So if we're going to get an accurate age of what's going on in our solar system, we want to look at samples from all of the planets that we could possibly get our hands on. So we've done this. We've measured ages from rocks from the moon, rocks from Earth, rocks from Mars, any of the meteorites that come down, they try and get an age from any of those. We want to get ages from as many possible things so that we can really narrow down when this actually happened. We do this through radioactive decay. Okay. So, there are certain substances out there that do something which is called radioactive decay. These are elements that will change into some other kind of element or some other isotope of the same element at a certain rate. These rates are known. Okay, so if you start out, let's say, with 100% of something, over time, half of it will turn into its resultant compound, right? Its daughter compound, as they call it. Over another amount of time, another half will turn into that daughter compound, and so on and so forth. This amount of time for half of the original material to turn into the resultant material is what's called a half-life. If we know the half-life for certain kinds of compounds, which we do, we can then go to some random rock and figure out what percentage of resultant material to what percentage of original material is in that rock. And if we know those relative percentages, we can figure out where on this plot it is and figure out how old that rock is. So when we date all of the things that we can possibly get our hands on, we get a rough age of about 4.6 billion years. This means that the planets and the rocky material out there would have formed 4.6 billion years ago. This solar nebula hypothesis has done a great job of explaining all of the features that are out there in our solar system. So let's take a look at all of the different features and how this theory accounts for each. Okay, so first up is the disk shape of our solar system. Right? All of those orbits are in the same plane, roughly, and they all go around the same way. They all spin in the same direction. They move around in the same direction. This is a leftover from that disk shape we had, right? Remember, as that cloud contracted, it flattened out. It had all of the material going around in the same direction. So naturally, when little bits started clumping together to make the planets, they were also going around in the same direction. Okay, so the fact that everything moves in that same direction is a leftover from that formation. We've accounted for our two planetary types, our terrestrial and our Jovian, with that frost line, right? Remember, our inner planets are going to be made out of only that rock and metal that can condense there. Our Jovian planets, the outer planets, those are going to be made out of not just the rock and metal, but the ice and then the gas that they captured. So they become much bigger and much lower density. We haven't talked too much about this, the planetary rings and the satellite systems for our big guys. Because those big Jovian planets got to be so large, it's almost like they form their own little disk around them. And in that little disk around them, they got to make their own satellite system, right? Almost like a mini solar system within the solar system. Okay? Those little systems became their moon systems. Okay? Later on, then they added some of those ring systems. That was only possible, though, because these planets out here are so large. That large mass gives them that gravitational pull that they need to make their own little mini systems around themselves. We've also talked about the leftovers, right? Our asteroids, our comets, our meteors, all of that good stuff. Okay, these leftover bits are the kind of the remnants of what was going to go into the big planets that are out there. And then, of course, we have the common age of everything. If it was all made at the same time, it should have the same age. Just makes sense. So have we seen this going around with other stars? We have. Unfortunately, the planet forming process is a long one. So when we look at other stars, we can see there are certain stages that we can see, but it's not like you can look tonight and then look at the same star again tomorrow and see, hey, wait, there was a planet there that wasn't there yesterday. It's not fast enough for that. And in fact, even over a human lifetime, you're not going to see that happen. But we have seen these disks, right? All of these dark parts here, this would be the disk that would be forming those planets. Kind of exciting, right? Maybe there's some planets forming there right now. This is one of the latest pictures from the ALMA telescope. This is actually, there's a little star that's being formed in there, and you can see this is the disk. There are these lanes cleared out here. Maybe there's a planet being formed in some of those right now. But very exciting, right? This is one of the latest, I think this came out last year. Latest image of planets being formed around some other stars. Very exciting. This is just more evidence for the fact that this is an evolutionary thing, that planets arise naturally as part of this star formation process. This means planets everywhere, right? Those hundreds of billion stars in our Milky Way galaxy, a large percentage of those are going to have planets. It's just natural for them to have planets.